In this lesson, we'll examine the relationship between cell potentials and thermodynamics, and we'll be able to use cell potentials to find the Gibbs free energy for a particular reaction, as well as the equilibrium constant for a particular reaction, using the relationships that we've already examined, as well as some new relationships. So first of all, you know that the cell potential can allow us to predict the spontaneity. By being greater than 0, we know that the reaction is spontaneous. Now let's also keep in mind that for a spontaneous reaction, the Gibbs free energy is less than 0. And recall that the Gibbs free energy is the maximum amount of work that can be done by a particular system. Okay, now an example of the kind of work that can be done is electrical work. So what we want to do is find the relationship and determine the amount of maximum work that can be done by a particular electrical system. And there's a relationship that exists. It's negative NF E cell. And how this is derived is using Faraday's constant. And Faraday's constant shows us the amount of coulombs of charge per mole of electron. And we can use this in conjunction with the cell potential of a reaction, which is the amount of joules per coulomb, like voltage is the joules per coulomb of charge. So if we've got Faraday's constant, which is 9.65 times 10 to the 4, if we know the amount of charge in per mole of electron, and we know the cell potential, which gives us the joules per coulomb of charge. If we multiply that by the moles of electron that are transferred in a particular reaction, then we can determine the amount of joules, or the amount of maximum work that is available to be done by the system. Now, the reason for the negative sign is the sign convention of work, where a negative means that the work is done by the system. Keeping in mind, in perspective, connecting that back to an exothermic reaction. We know that an exothermic reaction is favorable, right? So it's the same kind of connection there with the sign. Now, we've got this relationship. We know that Gibbs free energy gives us the maximum work. We know that in an electrical system, the maximum work is defined by negative NFE. So what that means is that we've got this relationship delta G is equal to negative FE of a cell. And if we're dealing with the standard cell potential, it's G naught, and that would give the standard free energy of G naught from the standard cell potential of E naught. Okay, we'll look at the example on the bottom of page 21 in a moment. We're just going to extend our relationships here and look at how we can use this information to calculate the equilibrium constants as well. Okay, we know from our previous unit in thermodynamics that delta G naught is equal to negative RT ln K of C. Okay, that comes from the fact that Gibbs free energy is equal to 0 at equilibrium. And so knowing that, and knowing that Gibbs free energy is also equal to negative NFE, we can equate the two right-hand sides of the equation. Okay, so this equal to that, and we can solve for E to get this relationship between the cell potential of a reaction and the equilibrium constant for that reaction. Now this is in ln. If we convert it to a logarithmic relationship, and we also take it into account at 25 degrees Celsius, we can manage our R and our F and our T, okay, and simplify the relationship to E cell is equal to 0.0592 over n log of Kc, okay, and subsequently log of K is equal to n E naught over 0.0592. So let's look at these two relationships in action here. We've got this reaction, and it's got a standard cell potential of 0.320. In the first question, we're asked to find the Gibbs free energy of this reaction. Now, all the relationships that we have here require us to know the number of electrons that are transferred in the reaction. So you need to actually determine that. So in this case, you only need to look at one of them from the balanced chemical equation. I'm choosing to look at chlorine because it's the easiest to see. And you can see from the half reaction that the number of electrons that are transferred is 2. Okay, so the moles of electrons I'm dealing with here is 2. Okay, so my Gibbs free energy being negative NF E naught, I've got 2. Faraday's constant is 9.65 times 10 to the 4. My voltage is 0.320. Okay, and this actually comes out in joules because this is joules per coulomb. So I can divide by 1,000 to get the kilojoules. And as expected, for a reaction where the cell potential is positive, it's spontaneous, so our Gibbs free energy is negative. And to calculate the equilibrium constant for this reaction, and now that I've got the Gibbs free energy, I could use that, but I can also use my relationship that I just showed. Log of K is equal to N times E naught over 0.0592. And so log of K is 10.81. And then the inverse is 10 to the power of, so K is equal to 10 to the 10.81, which is equal to 6.47 times 10 to the 10. And as expected with a reaction with a positive cell potential, the reaction is spontaneous in the forward direction, so we'd expect it to have a large K value, which it does. Now we also have another relationship here that helps us to monitor the effect of concentration on the cell voltage. As from our previous lesson in galvanic cells, we talked about that the standard concentration is 1 mole per liter and the standard pressure for gases is 1 atmosphere for all cells, but there might be cases where you have concentrations that are different than that. So we need a relationship that it's going to help us monitor that difference. Okay? And again, we're going to use our thermodynamic equation. So we've got our thermodynamic equation of delta G is equal to delta G naught plus RT ln Q, where Q is the reaction quotient for the reaction. We know that delta G is equal to negative NFE, so we can substitute into this reaction, okay, for the E of the cell and E naught of the cell. Okay, and we get negative NFE of the cell is equal to negative NFE naught, so at standard conditions, plus the RT ln Q, where Q is the reaction quotient. Okay, now this is a bit of a mess of an equation, so we simplify it a bit by dividing through by NF. So we get E is equal to E naught minus RT over NF ln Q. And again, we simplify this further by taking into account the constants when we're dealing with 25 degrees Celsius, which is pretty standard. So I sub in my R, my 298, my Faraday's constant. We've got it shown with ln and log, so E is either equal to E naught minus 0.0257 over N ln Q or 0.0592 over N log Q. Okay, now what this is showing us is that as Q gets larger, so as we favor the products more, the concentration of the products is increasing. That's going to cause the E cell to increase as well. Okay, when the Q is equal to K, okay, the E is going to equal 0. Okay, so this relationship will eventually reach a point of 0 when we achieve equilibrium. Okay, so let's look at some examples here. Predict whether the following reaction will proceed spontaneously as written, okay, based on the given concentrations. So we're not just talking about standard conditions. So we can't just find the E naught. We need to use the Nernst equation to find the E of the cell at these particular conditions, and then decide if the reaction is spontaneous. Okay, so in this particular reaction, the cobalt is the anode and the iron is the cathode. So we need to find our E naught of the cell, and we do that by taking the cathode, which is negative 0.44, and subtracting the anode, which is negative 0.28, for a total of negative 0.16 voltage. So at standard conditions, this would not be a spontaneous reaction, but it is possible that changing the concentrations would lead to a spontaneous reaction. So we want to use the Nernst equation to find the E cell of this reaction. So it's E naught minus 0.0592 over N log of Q, which is the concentration of cobalt, over the concentration of Fe3+. Recall that pure solids will not be included in the equilibrium law as they have an activity of 0. Okay, so the E naught for this is negative 0.16. The number of electrons that are transferred, if you examine it, it is 2. Okay, and then we've got the concentration of the cobalt at 0.15 and the concentration of the iron at 0.68. Okay, so when you do the math here, you get negative 0.14 voltage, so therefore this is not spontaneous at these particular conditions. Okay, in this next example, you're given a galvanic cell, okay, and it's found to have an E cell of 0.54, and they're wanting the molar concentration of H plus for that particular scenario. So you've got the E cell, we can find the E naught. Okay, this is the zinc connected to the She electrode. Okay, so the She electrode is 0. Okay, minus 0.76. Sorry, minus negative 0.76. So the E naught for this is 0.76. This is one of the ones we saw early on in our galvanic lesson. So what we want to do here is use the Nernst equation to solve for the concentration of H plus. So E cell is equal to E naught minus 0.0592. Okay, the number of electrons that are transferred are 2 again. Okay, they're not always 2, just be mindful of that. Okay, and the reaction that's happening here is zinc, okay, and hydrogen over the hydrogen ions squared. Now, one unusual thing that you'll see when you're dealing with the Nernst equation is that with hydrogen, the pressure is in atmospheres and the other ones are in concentrations. Okay, so you've got 0.54 is equal to 0.76 minus 0.0592 over 2 log. The concentration of the zinc is 1. The hydrogen pressure is 1. So really what we're doing is rearranging this and solving for the concentration of H plus. And when you do that, the concentration of H plus is 2 times 10 to the negative 4. Okay, so these are a few key relationships. And we can see the connection between the E cell, the Gibbs free energy, and the equilibrium constant. Okay, it's important to keep in mind which one is spontaneous or favoring the product. So for Gibbs free energy, if it's negative, it'll lead to a positive E cell, a K value that's greater than 1, and all of these go together favoring the products. When Gibbs free energy is equal to 0 or E cell is equal to 0, okay, that's pure equilibrium where nor the products nor the reactants are favored. When Gibbs free energy is positive or E cell is negative, you know that the reactants are favored or that's not a spontaneous reaction, so that's going to have a small K value. And then this gives you the relationship, so Gibbs free energy and E cell relationship, Gibbs free energy and K relationship, E cell and K relationship. So you can move between all three of those variables.